This is Andy Barrett of polyphys.com introducing an app that calculates the discrete Fourier transform, or DFT, of a function. With lowercase t as the independent variable, you can simply type a function here and press enter. The function is graphed in the bottom left plot, which shows the full range of values used to calculate the DFT. The range can be adjusted by dragging from side to side, or by using padding. Changing the range of the function affects the DFT resolution, with higher range corresponding to higher resolution. This is a mathematical effect resulting from the fact that very small frequencies correspond to very large wavelengths. On the other hand, by adjusting how finely the function is sampled, we can affect the DFT's range. And this results from the fact that high frequencies correspond to fine structures in the function, and these can't be measured unless the resolution is high enough. The DFT is shown in the right plot with real and imaginary amplitudes in red and blue, respectively. These correspond to the in-phase and out-of-phase components at a given frequency. Thus, each amplitude is represented by Cartesian coordinates in the complex plane. The alternative is that the amplitude is represented in polar coordinates. We can toggle between these two options by clicking this button, where in the polar representation we have the option of adjusting the unwrapping threshold as well. The functions that you're allowed to use are shown on the bottom list. For convenience, capital T is defined as 2 pi times lowercase t. R and S are two constants that you're free to use in your function definition, and they can be controlled using these sliders on the top right. The Fourier transform is used to study the spectrum of a function. It takes a function representing the value of a wave at every point in time, and it generates a different function representing the same wave at every point in frequency. So you can use this app to understand what the DFT is doing, even if you don't understand exactly how it works. For example, if we took the DFT of a cosine or sine function, we'd expect to get a single peak in frequency space. Thus, a wave which is spread out in time is confined to a single point in frequency. The underlying principle of spectral analysis is that any function of time can be separated into these singular modes, which appear as either temporal waves or frequency peaks, depending on which representation we're looking at. Once you understand what the DFT is showing, you can use this app to study how operators applied to these pure modes affect the spectrum. So as an example, let's consider distortion. And I'll describe the physics a little bit. Say you have a metal rod and you want to measure how electrons in the rod move when you apply an alternating voltage. The alternating voltage results in a force on the charges in the metal, causing them to slosh back and forth along the rod's length. If the voltage oscillates like a simple cosine function, then the measured current in the rod will also be a cosine function, differing by some phase. Distortion will happen when the force on the charges is so high that they hit the end of the rod before the voltage reverses again. To imitate this effect, we can apply a function to flatten the cosine on the top and bottom. Any function that tapers off but is linear around 0 will work. I'll use the hyperbolic tangent function, or tanh, and I'll use r as a factor here to scale the sharpness of the tapering. As you can see in the spectrum, when the peaks start to flatten, the third, fifth, seventh harmonics start to appear, and the sharper this flattening is, the stronger those higher harmonics are. So what we learn by this is that the process that resulted in the distortion, which was this effect of the charges hitting this wall and being reflected, somehow this physical process is related to the appearance of these higher harmonics, and which harmonics appear can help us to classify the physical mechanism. In this case, the first harmonic that appears is the third harmonic, which is 3 times higher than the fundamental. The easy way to understand this is using a quantum mindset. We can imagine that there are these kinetic interactions between electrons in the material. When 3 electrons come together and interact, they can produce basically 1 electron with 3 times the energy, the kinetic energy that is. So these higher harmonics that appear correspond to this quantum merging and reseparating of energy in these higher order kinetic processes. So based on the fact that the lowest harmonic is the third harmonic, we can guess that the lowest order interaction is one where 1 electron interacts with 2 other particles. We could ask, why is it that this electron can't interact with just 1 particle? And it might be that these 2 other particles are a virtual pair or something like that. But what I guess I'm trying to demonstrate is this really bizarre effect that the physical mechanisms are linked to the mathematics. Anyway, that better be all I say about this app. Go to polyphys.com to play with this app and many others. And if you enjoy my work, then please spread the word or consider making a contribution to keep this project growing. This is Dr. Andy Barrett. Thank you for watching.